I do want to point out first is I did mention that everything gets posted to YouTube. So if you just go to blanket kind of YouTube, my YouTube channel is CGC Chem Mike, all run together as one word. Theoretically, you can search for it, and then you can find that channel. The next part, there are tons of videos. Every lecture I have ever given at Chandler Gilbert across the last 11 years of me teaching here are posted here, okay, for every class I've ever taught. So that's a lot of videos to sort through. So don't go through it video by video. Go to the playlists, and the playlists have it organized kind of by class and by semester. Yours is going to be right up at the front. It's probably going to alternate back and forth with 236, which I haven't created yet. So the lecture from yesterday, please don't play stop. Okay. If you haven't heard your voice already, it's generally not fun to hear it. Okay. Is there. So if you wanted to review, you could watch it there. The other thing that I'll point out is it is also in Canvas. And I've got the attendance thing up. Where did it go? The record, I'm not teaching all those classes. In Canvas lecture recordings. So Unit 1 lecture recordings. Oh, and I'll fix that real quickly. But it'll have the YouTube link set up there. You can get rid of it, no you won't. For each of those things. I'll try and update those general topics. Those were the general topics for last fall when I went through and uploaded the videos. That's roughly what was in those videos. Kind of make sense? Okay. So it should give you a little bit of structure on where those things are found. The PowerPoint lecture slides theoretically open here. Yep, it looks like they're opening the right set. I did notice that those, or that link shows up in a couple different places, and I may not have updated it correctly in some of those cases. So if you go through and you're like, but these slides don't look quite right, that might be what's going on, just let me know and I'll try and fix that link. Make sense? Which would then kind of take us to the lecture. Before we dig into it, do we have any questions that you want me specifically addressing right away?
For the Lewis X, or the lecture X Lewis structures, you had said stop at a certain point.
Yes.
And then do you
That's
want
not
to
you.
just submit that,
But
a screenshot of where you say stop, since we can't?
you can continue to move on there, and officially you're going to be responsible. It says stop for Chem 130. You are 230. So you do want to continue to advance through.
Okay.
We'll look at that. We'll probably look at some of those details today, actually. That's part of my plan. Kind of specific examples, in particular to the specific examples that we addressed or I asked about in that quiz on Monday? Yeah. So you do want to kind of push into that because it's going to talk about formal charge, and that's really important for us.
Okay.
Other questions? Okay. So, real quickly, again, kind of an overview. When we're talking about organic chemistry, it's really just what does carbon do? That's our primary focus. So it's what are all the bonding patterns of carbon? What happens when you bond it to something else? Does that change the chemistry? Does it not change the chemistry? If it changes the chemistry, well then we have to call it something different so that way we know it's different. And that's where you'll hear all sorts of functional groups and different names and things like that appear. It's because the chemistry has changed. Okay? We'll try that. Does anybody know of any functional groups? You know what proteins? Maybe let's try it this way. What is your end goal? What are you aiming for? For why? Why do you want a degree?
To have options,
To do what with the degree?
get a career possibly,
Which career?
dietetics.
There we go. Okay, cool. So we're in it for effectively nutrition and different levels potentially within that. And
Yes.
what is your goal? Why do you need the class?
Just apply to a program,
What program?
medical lab science.
Medical lab science? Okay. I don't know anything about that, so I might ask you more questions about that later.
Dietetics.
Dietetics?
PA school.
PA? Okay.
Dietetics.
Dietetics?
PA school.
PA school. To the PA schools, make sure you've checked to ensure this class actually works.
Yes.
Sometimes it does, sometimes it doesn't. So you may limit some of your options. Just be aware of that. Okay. As far as I know, it should be fine as far as dietetics, and that was 3 dietetics? Okay.
It is.
Okay.
Double check.
It should be okay, yeah. And then I don't know anything of medical, you said lab assistant?
Lab science.
Lab science. With, that's the program?
Yes, that's the program in ASU.
Oh, okay. For what end goal?
We're gonna work in the lab at the hospital. We're gonna
Okay.
blood bank, chemistry testing,
Okay, okay.
methodology.
Okay, then yeah, this is probably correct for that.
Yeah.
And one of the reasons that I bring this up is to try and test to see what your background knowledge is. So we've got 3 people in dietetics, 2 in PA, blood. Does anybody know anything about lipids? Ish, we got some issues with lipids. Do you know anything about functional groups in lipids? Stretch. What makes a lipid? Let's try that.
Fat.
Fat. Well, what is fat?
You mean triglyceride?
Okay, triglyceride. What's triglyceride?
The bad one.
None of them are really bad. It's always bad when you have excess. If you put excess of anything, it's problematic. Everyone goes, oh, water's not a problem. You drink enough water, your brain explodes. Like, anything can be bad.
Yeah.
So, what is a triglyceride?
Saturated fat.
Ooh, I like the word saturated. What is saturated in reference to?
The saturation.
It's okay. Hydrogen bonds, which is another word that we're going to throw into this. So that's good. We're getting those. Hydrogen bonds becomes a really dangerous word because it can mean a whole bunch of different things. So when we're talking about triglycerides, typically what we're talking about triglycerol. Oops. I had to remember the structure real quickly. Artistic interpretation. Does that vaguely ring a bell? Have you seen triglycerides? It looks something like that. Okay. What we're seeing with that, number one, is Lewis structures. We're also seeing electrons, which universally, blanket statement, everybody in this classroom needs help with electrons. That's okay. Okay, but we do need to make sure we review back on that. So there's lots of implied information in there. And that context has a lot of stuff that we have to dissect and pull apart and learn about. So, for instance, this part out here, we might call saturated. Well, why do we call it saturated? We call it saturated because what's out there is just a bunch of carbons, and those carbons, continue, all have hydrogens. So when we say saturated, we said we've taken carbon's bonding patterns. Carbon has 4 maximal amount of bonds. We've put as many hydrogens as we can on that carbon with all single bonds. So what happens if we unsaturate it? So you're right, it referenced the hydrogens. If we unsaturate it, what does that mean we have to do?
Take away the hydrogens.
But if I take away the hydrogens, what happened to the bonding pattern for carbon? How many bonds was it supposed to have? It went by real fast. 4. Does it have 4?
No.
No, so something went wrong. What went wrong is when you replace or remove those hydrogens, you must replace it with another bond. Okay? That different bonding pattern changes the structure, it changes the functionality of the molecule, and because of that change, we now want to address it. We come up with names for it. We move out to the kind of biological systems. This is where you hear saturated and unsaturated. Okay? Because what they're referring to is not so much the functional group, but the end result of that functional group change. What are the physical property changes behind it? When we look at the functional group, if we're just looking at saturated carbons, we would call those alkanes. Okay, so you hear alkanes a whole lot. They're the backbone of pretty much everything. As soon as we go through and remove 2 hydrogens and now replace it with a double bond, we've changed the bonding pattern of that carbon. And it's changing the chemistry. Because it changes the chemistry, we need a new name. So we create whatever name we want. So when we talk about all of the terms that get floated out there, they're just names that someone sat down and said, no, I'm going to call it Bob. So everybody calls it Bob for the rest of their life. Right? That's just how it works. Okay? There's some logic and reasoning behind those systems, but for the most part, they're just arbitrary systems. Okay? If we make it a double bond, we now call it an alkene. Instead of an alkane, we call it alkene. Note, there was a common root within that, alk. What is the alk referring to? What did those 2 structures have in common?
Carbon and hydrogen.
Yeah. So what we're talking about is it's some kind of carbon structure, okay, that we've changed the bonding pattern behind it. Okay? So when we're talking about those larger pictures, there's some chemistry underpinning all of that. And that chemistry underpinning has to do with the different functional groups. Over here, it's no longer just carbons and hydrogens. Clearly we have another symbol. We have an O. Okay? What was the O?
Oxygen.
Oxygen. Is oxygen going to change carbon's bonding pattern?
Maybe.
Okay, maybe. And when it does, that changes its chemistry. Therefore, we need a new name. Okay? So what we have to understand is kind of not just, oh, carbon's supposed to have 4 bonds. Oxygen's supposed to have however many bonds. Right? Because at this point, I'm not super picky about knowing that. Okay? What we're trying to figure out is just what are those bonding patterns when we start putting those things together? How does that change the chemistry? The more we understand how that changes the chemistry, that's how we can start to say, well, now I have saturated fats and unsaturated fats. Okay? You start to kind of scale up from that. So OChem is kind of like looking at the weeds for all of your background. Okay? So you all have these larger kind of big picture ideas of what's going on. OChem is now saying this is the nitty-gritty detail behind why those things function the way they do. Okay? Why has that become important for you? What are you going to do with that? Okay? If you're going to drill into the hardcore details behind that field, okay, be it PA or dietetics, okay, or blood typing stuff, that's the best I can come up with that, okay, you need that weed information. But maybe you don't. And at this point, we have no clue. Okay? So the people in those varying branches said, since we don't know what you're preparing for, we need to make sure you're prepared for all of it. Here's your access. You now have to take the weeds classes, even if you aren't going to use it later on. Kind of make sense? Okay? And it's going to happen again when you move up to your more advanced systems. They're going to make you take more detailed classes. Because again, they want you to have that breadth. Okay? So within OChem, we just want to know what makes these things up. Okay, so if we clear that all away for the moment, okay, it's just the study of carbon compounds, and it's then kind of by corollary, what does carbon typically bond to? So that becomes our primary focus. So we talked really briefly on Monday and in the Intro to Everything video that we condensed the periodic table down. When we condensed the periodic table down, pretty much what we got rid of are all of the atoms that don't bond to carbon. Okay? So we don't need to worry about those. The only ones we need to worry about are the ones that bond to carbon. Right? And there are some kind of gray area exceptions. The more we do research within organic chemistry, the more we can discover that carbon can make bonds to those other elements. We just don't use it that often. So there's other limitations that come into play. Okay? So we've got carbon. We want to know how it interacts with other elements. Okay? When it interacts with other elements, what does it do? If we're talking about saturated and unsaturated fats, okay, what you're concerned about is how they stack ultimately. What do I mean by stack? Do they congeal and form a solid, or do they stay liquid? Because those have very different properties. Okay? Particularly if you collect a whole bunch of them, say, in your bloodstream. So we want to understand what's going on with those, and that's why you'll hear sometimes bad fats and good fats. Okay? Generally a bad idea to have solids in your blood. Okay? That doesn't mean they're bad, we just don't want to accumulate a whole bunch of them. Okay? So we're looking at those larger structures. Well, those larger structures can be compounds. When I look at the bonding characteristics within, of course I got rid of it, that drawn molecule of our triglyceride, we were looking at the bonds. That makes it a compound. When we're talking about a group of those things coming together, they aren't forming chemical bonds. They're just kind of getting near each other, and they're attracting to each other. That's not forming a chemical bond, that's forming a larger macro structure. Okay? That macro structure follows the same principles, it just doesn't move quite as far along the path of making bonds. Okay? So where we want to start is first off, what are our elements? What identifies those elements? Then what becomes the most important part of those elements for us now building these larger structures? Once we know our elements, we can then advance to say, okay, now let's make compounds. Let's make these molecules where we actually have those connections. Then we have to say, well, what does it mean if it makes those connections? How would that change how they could interact with the potential world? Once I understand that, now we can move into saying, okay, can I get chemical reactions? Am I actually going to change bond structures when I bring these things near each other? Okay? So our primary first unit is just what are these structures and how can I draw them simply? Okay? And actually, I shouldn't have erased it. Go right back and draw it out again. When we talked about that triglyceride, you might have noticed that I already started making changes in my drawing. So what are some things that you've noticed in this drawing? Particularly even when I added a little bit more detail. What do you see? Since you're quiet, I'll give you the easy thing. You picked red and green, Mike. Those are the two colors you picked. Yep, you're right. Good observation. Try again.
It's a chain,
What's a chain?
the triglyceride part, or
Which?
the squiggle is, it's a chain.
Ah, the squigglies were carbons and hydrogens all connected to each other. Why did I not show carbons and hydrogens all the way through this?
Because there's a lot.
We're lazy. Okay? So we need to make simplifications to our drawing so that we don't have to draw all of that gory. There's no way in hell I'm going to draw all those carbons and hydrogens. Okay? That's just not something I want to do. So I want to come up with simplifications behind it. Okay? So what is some of that simplification? It's not just squigglies.
Like structures. Like it's a very specific shape you use to
Ooh,
determine.
what shape did I use?
Big.
And I know they're a little bit crude, but for record, I didn't do this, right? If you take biochem, that's an actual different structure. Different story. What shape did I use? A little bit crude. Should I clean them up a little bit? Think that might make it easier? Yeah? Okay. They aren't that horrible for the record.
Way better.
Triglycerides are longer for the record, but what shape did I use? I mean, I kind of agree with that, but a triangle would be this.
Yeah. Not.
I've never heard mountain range. That's not where I wanted to go, but that works. Mountain ranges. Okay. Typically, we'd reference this as a zigzag.
Okay.
But if we go here, I'm showing straight line. Why?
Because it goes up and then down and then up.
Why does it go up and then
There's a
down?
specific term for it,
Yeah, that's good.
and it's on the tip of my tongue, but I can't think of it. There's one that it'll go in this way, and then one where it like does the S.
Isn't it just when carbons connect?
I think I know what you're talking about, but that's more advanced than you actually want to bring in here.
When carbons are bonded together, isn't it the angle is supposed to be?
Here, we aren't really showing a shape. We're just showing the connection of those atoms. Here, we're showing a shape. Okay? So we've decided to adjust our drawing. What if I had just drawn it as a straight line? Would I have been able to do that here?
It would have been the same thing.
Okay. What do each of those points mean? Mountains versus valleys. Ooh, close. Not a carbon bond, but the point is not a carbon bond.
Where the carbon is.
It's where the carbon is. What is the line?
The hydrogen.
Bond.
The bond. Okay, just like here. The line represents the bond. That's still constant. Okay, we're going to come back to your hydrogen in a second. Okay, so you notice I put zigzags all the way through there. Okay, how many carbons do you think are identified here? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 points.
Should there be 12?
You're trying to make it a real triglyceride. Stop it. 11, 12. Okay, so there's 12 points to get our real triglyceride. Okay. What if I had drawn it like I had drawn this one? Straight line. What is it going to look like?
What do you mean?
A bond. It's like a big
Oh,
bond.
yeah.
Ooh. I can't see where the carbons are in a straight flipping line. So I bend it. That allows me to see and be able to count those carbons along the way. For the record, I could go through and be like, well, there's 1, 2, 3, 4, 5, 6, 7. That's going to be pretty tedious. The whole point was to make this as fast as humanly possible. The zigzags help with that. Okay? So the zigzags visually help out with that. There's also more information embedded behind that we'll learn a little bit more. Okay? You mentioned hydrogens. Let's go back to the zigzag because this line is killing me. And I'm not doing 12. Where did the hydrogens go?
They're above the peaks and valleys.
You mean you see hydrogens up here?
Well, that's not like a true structure where you have it all drawn out. But wouldn't that be where they are?
Oh, that's getting a little elitist. A true structure?
But like, it's like you said, like that's just a shorthand of it, but you know that there's actually hydrogens there.
Cool, I like that. We know that there's hydrogens there. How do we know there's hydrogens there?
Memorization.
Sort of. Okay. Would you say it was memorization that the points were carbons? Technically it is, but does that seem like a little bit of a stretch to just say points are carbons and now you've memorized that fact? I mean, to me, that feels a bit of a stretch of the term memorization. How many hydrogens are on that green carbon?
2.
How many hydrogens are on, whoops, not green. Let's make that purple. I'll get out of your way in just a second. That purple carbon.
3.
Why did it change?
Because it's missing a bond. Well, it would be missing a bond if it didn't have 3, because it ends.
Ooh, okay. So how many bonds was it supposed to have?
4.
Did we say that already?
Yeah.
Yeah, carbon has 4 bonds. It needs to have those 4 lines somehow around it. So one of our approximations, or we've now addressed 2 really big approximations or simplifications in our drawing, carbons will be points. Okay? That's how I know I have a carbon. It's a point, okay? Which means the end of a line. Hydrogens, I don't want to show. That's a lot of work. So I will imply hydrogens. When we imply hydrogens becomes dangerous as a concept, but for the most part, we only imply hydrogens when they're connected to carbon. Right? Which is kind of nice because carbon's the one that has the most possible bonds. Everything else has less or fewer bonds, so we don't have to specify as many hydrogens if we drew out those structures. Okay? And since we know carbon's supposed to have 4 lines around it, when I look at that green point, it already has 2 lines, which means I need 4. I have to have 2 hydrogens. If we look at the purple spot, I kind of erased it a little bit, it has 1 line, which means there are necessarily 3 hydrogens around it. Okay, to satisfy that proper bonding structure. Kind of, sort of? Okay. Where does the proper bonding structure come from? Why must Corbin, sorry, it's my son's name, carbon have 4 bonds? Oh, satisfy the octet. The octet is now looking at what, though? What is your octet? 8 electrons. Okay? So if we're looking at just carbon, we started to push and just say, here are these things to memorize, but where are those things coming from? Because we could go through and say, these are the things we got to memorize for oxygen. These are the things we got to memorize for nitrogen. These are the things we got to memorize for chlorine, for bromine, for iodine. But if we understand why carbon has those components, we can now apply that to all the other atoms. Kind of make sense? Okay, so you're right. It has something to do with electrons. So what we should double back to is go, well, cool, we've got this big idea. Now we got to drop to the weeds. What makes a carbon atom? Okay, and we can cheat a little bit because I don't care about all aspects of what make carbon a carbon atom. I only care about octet, and octet was in reference to electrons. So really I only care about electrons. Okay, so if I'm looking at carbon, how many electrons does carbon have? And if we're trying to figure that out, that becomes a really challenging thing to do without a flippin' periodic table, which I was going to attempt to resolve and then didn't. Okay. So we could look at a periodic table and try and say, well, how many electrons does carbon have? Okay. And in the grand scheme, the answers of both 6 and 4 are acceptable answers. Okay. Which is kind of a nasty statement to make. Okay. Because it didn't specify really what electrons I wanted to look at. I just said, how many electrons does it have? And if we're going to really push to the true answer of that question, 6 is absolutely correct and 4 is wrong. Okay? Because if we look at this, these numbers represent officially the number of protons. So for carbon, it's got 6 protons. And when we think about carbon and answering how many electrons it has, we start at the simplest case where it is perfectly balanced and neutral. Protons were what charge? Positive, and electrons are negative, which means to completely balance out 6 protons, I need 6 electrons. So answering 6 is a phenomenal answer. It's not a useful answer, though. The useful answer comes into play when we talk about the valence electrons. So now we have to differentiate. Okay? And what that's now coming back to, get out of this. Come on. Is where our electrons are located. Our electrons are located at energy levels. So on that periodic table, you notice that we've got a bunch of rows. Right? It's effectively a grid. We've got rows this way and columns this way. Okay? Those rows represent energy levels. For those of you curious, hydrogen's not shown in the first energy level. Why not? Because hydrogen and helium just do weird, goofy stuff. Okay? So this periodic table is actually a nice one because they pulled hydrogen off because they didn't want you using hydrogen to create patterns behind it because hydrogen and helium just screw up the rest of the patterns. Okay, they're too small to really have any solid meaning behind them. Okay? So second energy, third energy, fourth, fifth, sixth, seventh. So if we were to go through and look at carbon, carbon has 6 electrons. I have to place those electrons into the appropriate energy levels. Okay? So here's where we could say we have our energy levels. The lowest energy level is going to be our first, and then it starts to go up. Is that confusing? Periodic table, we went down, but here we're talking about up. I would say that is, for the record. Okay? But that's kind of what we're referencing. So how do I place those electrons? Do I just say we'll use red? 1, 2, 3, 4, 5, 6? No, why not?
Because it's the circle and there's outer ones and then inner ones.
Okay, so I'll work with you on that. Okay. Really hate the bio taught you that, but we'll work with that. Okay, circle. Here's the circle. There's, I'll even color code it. There's 1. There's 2. 3. Yellow's not going to show up well. There it is. Yellow. Come on, work with me. Orange. And then we can drop in our red. And if I draw in my electrons, I'll switch to dots now. 1, 2, 3, 4, 5, 6. So your argument was this is wrong because it doesn't show circles. Well, here's circles.
Well, you can't do it just one on each one. You have to do a certain number on each.
So when we talk about the electron locations, this becomes something that I would completely agree is a memorization, because where it's coming from is quantum mechanics and crazy physicists and mathematicians that go through to try to define where an electron is located. Okay? And ultimately, we can't say an electron is here. We can say it is here. Okay? The probability of finding that electron in that space ends up coming down and breaking into these mathematical principles, and within those mathematical principles, it starts to say how many electrons can go at any given stage. Okay? And where we place those electrons initially is in what we call orbitals. This was an energy level, not an orbital. So I can't place any electrons into an energy level. Okay? Which is why this circle thing is a bad idea, because what they're showing is energy levels. That's wrong. Okay? I would need to place it into an orbital. So the quantum mechanics come through and say that for each energy level, we get a new orbital type. So for our first energy level, we start with one orbital. That one orbital is an s orbital. Okay, that's what we talked about on Monday. We move up to the second energy, we copy. We get the same orbital type, an s orbital. But then we get a new type. We get a p orbital. Move up to the third energy, which is green, which is not in my palette, so let's get that in. S, P, D. Okay, vaguely ringing bells from what you remember from 130 or your Gen Chem classes. Okay, that's what's happening within those. If those were indeed orbitals in and of themselves, we could then try and place electrons in those. And if we scaffold this all the way out to our 6th or 7th energy level, what we would find is we have not placed enough electrons to explain this. I might be able to define the location of 30 to 40 electrons. Well, where the hell are all the other electrons? Okay? And that's because I said not orbital, I said orbital type. Because another thing that falls out of all that mathematics is it's not just orbital type, but also orbital orientation. So we would start with a type, whoops, let's get that black back in there, our S, but then that moves to an orientation. The orientation is now where we lock down our orbital. Okay? The orientation is quantum mechanically really messy and fuzzy, so don't stress a whole lot about that. For our purposes, we can keep it relatively simple. Okay? That comes into play when we know what the orbital shape is. Okay? And the shape is defined by our orbital type. So the s orbital type has what shape?
Circle, sphere.
It looks like a circle, but, and this becomes one of the nasty things within OChem, it's three-dimensional, it's a sphere. And if I have that sphere and I spin it and rotate it, I can't tell a difference, which means there's only one orbital. Okay? If I move up to the second energy level, it's still the S type, which means it still has that one s orbital. Okay? For the record, I'm drawing it smaller. That's wrong, because larger energy, I'm just cramped up here. I'm trying to cram more things in there. Okay? We move up to the P type. It has this dumbbell shape. The dumbbell shape introduces a new issue. That new issue is that I can tell when it is rotated. Okay? So it has different defined orientations. Those orientations align along the x, y, and z axes of a coordinate plane. Okay? So you'll sometimes see people draw usually the x and the y pretty well. And then if you're watching somebody attempt to draw the z is the one coming straight out of the plane at you. That's not easy to draw. Okay? Textbooks can do a better job presenting that. You okay? Just checking. It looked like you were thinking about it. I want to see if there was a question there. Okay, we good? It's all the reflex. Okay. So what does this now mean for us? Okay, well, this is as far as we really need to go as far as OChem. We could continue to go on, look at the d orbitals, and I'm not even going to attempt to draw those. We could look at F, which are even worse, okay, or pretty, depending on your perspective. Okay, but really our focus is just in here. So if we simplify this and we talk about all of these orbitals, I could call that first orbital down here, it's an s orbital, but it's at the first energy level. So I could call that 1s. The next orbital I could call 2s. The next orbital I could call 2p, that's a 2. I'm going to follow the order I have, 2py, 2px, 2pz. Are we okay having memorized that there's 3 orientations for the p-type? Okay. If we're okay with that, we can condense those down into just 2p. Okay. But if we do that, we're going to have to remember another piece of useful information. Okay. If we're talking about electrons, and I place one here and one here, what happens when I place one in the 2p? Let's say I can only place one in each. Let's just start with that. I place one here, I have 2s1. I can reference the number of electrons within it. 2s1, I can only reference the number of electrons in it. If I have 2p, what numbers could I put?
Don't you have to fill the 2s first?
We'll get to that in a second. Okay, fine. We won't get to that in a second. You guys are going to be ahead of me. That's fine. Each of those orbitals can hold how many electrons? 2, which is why we could say 2s2, 2s2. We could then say 2s2 for the 2py. But we could also say 2p2 for the 2px. I'm not even going to try and dissect what I just said. 2p for the 2pz, I could say 2pz2. Which means if I'm going to abbreviate 2p, instead of looking at the x, y, and z, I have to remember that that's going to be 2p6. Make sense? Those are now the maximum amount of electrons that I could place all the way through that. Okay? Just for giggles, you said octet. What does octet mean? 8. Cool. 2 plus 2 is 4, plus 6 is not 8. Something weird is going on here. What's a weird thing going on? Okay. If we're talking about octet, we're talking about making bonds. So I take one atom and another atom and I bring them near each other. What's the first thing that's going to interact? Well, what makes one atom one atom?
They're protons.
Protons. Is that it? They only have protons?
Electrons and neutrons.
Ah, there's 3 things. There's 3 subatomic particles. Where are those 3 subatomic particles?
The
If they're floating around and I bring them near each other, then any of those three particles could interact, right? That would make things really hard. Are they just free floating around?
Aren't the protons and the neutrons like in the nucleus center right there?
When we look at an atomic structure, protons and neutrons are jammed into a nucleus. An itty-bitty marble inside the superdome. Okay, and if you haven't heard that analogy, we talk about the size of the nucleus. If we made the nucleus a marble, your electron cloud would be the superdome around the marble. Okay? So if we're talking about size of particles, protons and neutrons are very, 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 very small. Electrons are on the outside. So if I now take atom A and atom B and I bring them near each other, what encounters first? The electrons. My problem becomes simplified. I don't worry about the protons and neutrons. I only worry about the electrons. So cool. In this case, I've got 10 electrons that I've got to worry about. Are all 10 of those equally likely to interact when I bring those two atoms near each other?
No,
No. Why?
because,
It's hard. You got it.
well, depending on what the elements are that you're bringing together, they're gonna eat it, no, okay.
Nope. Doesn't even matter what elements we bring together.
Because some are gonna dump their electrons and some are gonna steal their electrons.
The next level.
Just the valence, like whatever's in the valence.
If we're looking at these electrons, we said it was 1s, 2s, and 2p, right? And if we look at where these are located energy level wise, the energy level has a lot to do with the size of the atom. It's where those electrons can exist. A 1s energy level is very low energy. It's contained to a seat. We can still move the seat around a little bit, but that's relatively limited. The 2s energy level can now maybe stand up. As standing up, they can move around a whole lot more. They're occupying a larger space. Well, what does that mean for us? If I'm now bringing those two atoms near each other, the thing that's going to interact first is the highest energy level. Right? So if I'm looking at these electron configurations, I don't care about the 1s. Those aren't going to be relevant. And why does that become important? If those aren't relevant, what can I do with those electrons? Ignore them. And why does that become so powerfully cool? How many electrons do we have left? 8. There's the octet. The octet is coming from looking at that outer energy level. And if we're talking about like expanding things out, well, what happens when we move to the third? Stop it. That's a different class. Don't worry about it. Just focus on the second. Okay? So cool. We've got these kind of valence shells. So one of the things we might want to be able to do is to be able to say, hydrogen, what does it look like? Okay? And if we know that fast, we don't have to do all of this analysis because you probably don't want to do this ever again, right? There's a confident answer. Okay, I'll put that on the test because we want to do it again. We want to be able to look and say what's that information as quick and easily as possible. And this is where the periodic table has encoded a lot of that information for us. Okay? What we were talking about on Monday, this was called the S block. This was called the D block. Do we care about the D block? Nope. All we cared about was S and P. So what can we do? And it's gone. Okay? This was called the F block. Do we care about it? Nope. Also gone. And then this last one is called the P block. So those are our primary focus. Those are the ones we care about. Interesting little bit of tidbit. Where is carbon? It's in one of those blocks. That's why we study it. It's part of that system. Not only that, which energy level is it? The second energy level, which means it matches this 2s2, 2p2. Well, why is we now going 2s and 2p? And how many numbers should be going after those? Okay. So we have, whoops, I meant to write 2s. 2s, and we have 2p. When we talked about it initially, we said that was not supposed to happen like that. 2s2 and 2p6 was our maximum. Right? So 2s2 was the amount of electrons we could fit into the s orbital of the second energy level. How many columns are there in the s2? That's where it's coming from. The periodic table has that organization built in. When we move across, because we're now moving through our second energy level, the very next element's going to hit us with boron. Okay, and that's now part of the p block. Okay, 2p6. How many columns are in our p block? There it is. Okay. If I look at the amount of electrons I've defined here, 2s2, 2p6, I'm putting 2 electrons in here, so that one's full. I'm putting 6 electrons into my p block, which means I would be looking at neon. Neon is our noble gas. And the nobility are all hoity-toity jerk-offs that don't want to deal with the rest of the world, so they don't interact with anybody, as I believe you had suggested Monday, right, Kimball? Yeah. Okay. They don't want to interact. Why not? What do they have? Why are they stable? Ooh, there it is, an octet. They have that row entirely filled with electrons. Okay. So what does that mean as far as we're concerned? We can mostly ignore that column. I don't want to entirely delete it because I want that octet memory still in there. Okay? But we're not going to do anything with those elements because they can't interact. There's no place for them to share electrons with something else. So let's go back to our favorite carbon. How many electrons should we do for carbon? Well, if we start, it's over here, so I have to fill these up first. So if I'm going to look at carbon, I'm going to go 2s, 2, then what? 2p, 1, 2. It's in the second column, and I get 2p, 2. Okay. How many bonds did we say carbon had? Because you jumped on that right away. 4. Okay. And we said octets were important. How many electrons have I defined? 4. How many electrons do I need to get to an octet? 4 more. Where are those coming from? The 4 bonds. Okay? That information is buried within this. Okay? Again, I don't need to know the specifics of what orbitals are contributing to this, but I do need to know how many valence electrons there are, because that can help me predict the bonding patterns. Okay? So we just walked through carbon. What would I expect if I switch this up to oxygen? Well, oxygen, also on the far right, so 2s2, 2p4. How many valence electrons does it have? 6. What does it want to get to? 8, which means 2 bonds. Nitrogen. I did it again. 5, which means 3 bonds. That information is encoded for you. It's not this new thing that you have to memorize. It's already there. Okay? But that was also doing all this orbital stuff. Did you like the orbital stuff?
Yeah.
Okay, you didn't like it. Some people like it. Cool. If you like it, keep using it because I think it's neat too. You don't like it. Okay. Does the periodic table have this information for me so I don't have to worry about it? What's the Roman numeral IV mean? 4. How many valence electrons did carbon have?
4. 6. 6.
I don't know why I go carbon, oxygen, then nitrogen. But I do it every single time.
You do YXC too.
Yeah. But the Y is nice because it's up and down. Like, I think that's why I do that one. I don't, but neither here nor there. Okay? So that information is encoded in the periodic table. We really just need to know what the valence electrons are, not necessarily the bonding patterns. Okay? The valence electrons allows us to predict beyond our limits. The bonding patterns now only allow us to focus on that one aspect, okay? Which is okay. And for this course, knowing the bonding pattern is probably enough. Okay? There will probably be cases that'll pop up where you're like, oh, I needed to know the electrons. Like, okay. Kind of, sort of? We feel a little better about electrons? Would hope so. Not always, but. Okay. So when we talk about this, this is why I give you this. Okay? Because it really just zeroes in on the critical elements. Okay? But as we went through and talked about doing this and finding electrons, and I finally got this, I think I got this one up for you guys, being able to predict, this is missing some critical information. Okay? Those Roman numeral pieces aren't there. You would have to kind of count them out. Okay? Do you think having those numbers written across the top would be all that particularly valuable to you? Okay. What are you, at this point, it probably shouldn't matter that much because you now know where it's coming from. Okay. Which is why I think for the most part when this table was first put together, we just ignored those numbers because we're like, oh, people already knew it. Like, we don't have to stress about it. Okay. But that's what this table is supposed to do, is just give you the rough setup, and then you should kind of overlay that extra information. Kind of, sort of? Okay. Should we now try and make it more challenging? Okay, because that's just atomic. Okay, and the whole point of the class is how do these interact on a much larger scale, which means I have to take each of these atoms and I have to interact them with each other. Okay. Multiple theories go into how we build them out. Okay. Officially, I believe it actually started with a guy, Kekulé. No idea if I'm pronouncing that right. That then Lewis took over, and Lewis further developed it, and Lewis gets most of the credit, I think, for structures, to the point where we call them Lewis structures. Okay. There's rules on how you should go through and draw Lewis structures. Okay. 2, 4, 6, 7. 6 of you in this classroom were probably taught bad rules. Okay? All 7 of you have probably forgotten the rules. Okay? Yeah?
I'm a fresh memory today, so I know.
Oh, okay. Touche. Okay? This is the system that you should start with. If we talk about what you guys did on the quizzes for drawing these things out, you had amazing reflexes. Okay? I got a lot of people drawing things like this. Okay? For that first one. Some people, I think, left off the positive charge. This gets to that part in the Lewis video where you need to continue because we have to specify the charge for the atom. Okay? So that is a difference, because if you took Chem 130 at this campus or at Chandler Gilbert, that's what you were taught to draw. Okay, for that particular structure. Charges get assigned to the molecule, not to the atom. If you took 151, both of you took 151 and 152, you may have been given more information. I would hope you were told that you needed to assign it to the atom. You may or may not have been. Okay? But that's something that we would specify. Okay? So in and of itself, that's okay. But what I didn't see people write down was that carbon has 4 valence, hydrogen has 1 valence. There's 3 of them there. I need to put 7 electrons into my drawing. Okay. Whoops. I also need to remember that that charge, whoops, come on, pen. That charge being positive means I have to subtract 1 electron from this, give me 6 total electrons. So that when I draw my drawing, 6 electrons go in. Where are the electrons in this drawing? Okay? And this is where sometimes we have that context and sometimes we don't. When we go through and draw out our structures, my recommendation is you get your valence, you pick your center atom, carbon, we scatter our hydrogens around the outside, and then we place our valence electrons, this is our count, into our drawing around that center atom. There's 2, 4, 6. If I have a pair of electrons between atoms, I can convert that pair of electrons into a line representing a bond. Okay? I get the exact same structure, but it's the thought process that goes behind it. Why is that thought process so critical? C2H2, most people screwed up. Okay? And they screwed it up because what they went to was this reflex of I can just draw lines to represent my bonds and just draw it out and hope it works. Okay? They also screwed up the first one that I didn't include on here, SO3. Okay, there were a couple people that were able to actually draw out a decent structure for SO3, but were also wrong because they didn't take into consideration the amount of electrons. So those electron counts become critical to drawing a proper structure. Kinda, sorta? The issue is that when we move to more complex structures, you just drawing lines usually results in screwing something up. Okay? So you have to understand kind of those valence electrons behind it. And where we start is with relatively simple structures as we build this out. Okay? And then we understand those bonding patterns so that we can skip and never have to worry about those directions ever again. Kind of, sort of? What we'll also find is that when we move up to all of these structures, they become significantly more difficult than most of the structures you've had to work with, the CH3 and the SO3 that I deleted. Okay? These first two had clear center atoms. If I have a center atom, that allows me to define everything around it. None of those have clear center atoms. So how do I build out those structures? Okay? With the C2H6, I think I saw some people starting to work it out where they did this, and they were like, ooh, I know I want 4 lines on it. You may not have known why, but you got there and went, that's not good. So there was a eraser mark, and they put another carbon, and then threw the other 6 hydrogens on. Okay, that's fair play because you're not understanding the reasoning behind it. You're just kind of building it out and hoping for the best. Okay. When we move to the next one, okay, you went, I learned my lesson. I'm not going to just draw all the hydrogens straight on it. Okay, and I got a lot of people giving me this. What's the problem with that?
Doesn't have more.
Okay, we're missing those 4 bonds. Okay, I don't personally like referencing it as 4 bonds, so I'm a little bit peeved at myself for allowing that to happen. I like referencing it as octets. Okay, but the 4 bonds works, but we're missing those 4 bonds. Okay, I think I even saw one person do something like this. They're like, I don't know what it ends at. This has some meaning to it that we already talked about earlier in the class. When I have a line, it ends at a point. And if it ends at a point, what does that point mean? Carbon. So by drawing that, really what you're saying is that there's another carbon down here and up there. And we didn't want that. Okay? So we don't have just lines going to nowhere. The lines have to go to something. Okay? But what you were at least acknowledging is that you were missing the octet. Okay, so let's try the rules on this. Carbon has how many electrons? 4. There's 2 of them, right? Hydrogen has 1. There's 2 of them. 10. Did you say 10?
10 total, so that's what I meant.
I'm going to blame you, but I think I was doing that in my head already too. Okay, 10 electrons. How many electrons have I drawn?
6.
I haven't drawn 10. I need to have 10. So how many am I missing?
2 more lines.
And this becomes an interesting teaching thing. 2 more lines becomes a dodgy statement to make because it could mean that I just put 2 dots on an atom that don't turn into a line. Okay? And we might see that, I think we'll see that when we look at this one. Okay? Lines mean very specifically in my language, bonds. Okay? Maybe what you're about to interpolate is going to result in a valid structure, but I want to slow that roll just a little bit. Okay? I need 4 more electrons. Where should I place those 4 more electrons?
On the carbons.
Okay. We want to place our electrons onto atoms because atoms own electrons. You're not wrong, but it's a process thing. Okay. So which carbon should I place the electrons on? In this process and argument, I place them onto an atom until I've achieved its octet. Okay? So I'm going to place both sets of those 4 electrons onto that carbon. Okay? I could have picked that one. It doesn't really matter because they're identical at this stage. Okay? And now what I would want to go through and do is convert pairs of electrons that are between atoms into lines. Since I don't have things between atoms, I don't want to convert those into lines. I want to see those as dots. Now I need to satisfy octets. Does every atom have its octet? No. Okay, hopefully what we see is this carbon is missing its octet. You might say, what about the hydrogen?
It only needs 2 to satisfy.
Hydrogen floated off the periodic table for a reason. It doesn't need 8 electrons, it needs 2. It already has 2 in that bond. So hydrogen is fine. This carbon's missing its octet. So what do I need to do? What does it say? Move pairs of electrons. So I'm going to take this bottom pair and I'm going to move it to that carbon. Now that carbon has more electrons, right?
Still unsatisfied above that.
Okay. It's still unsatisfied, but I've also created another problem. That one's unsatisfied. So moving the electrons from atom to atom isn't helping me. I need to move them somewhere else. Where do you want to move them? How about I move those electrons between the atoms? Now when they're placed between the atoms, that's a pair of electrons between. I can now say I want to turn that into a line. Okay? This leftmost carbon, 2 electrons in that line, 2, 4, 6, 8, still has its octet. How about the other carbon? Still missing 2. So what do I do?
3 lines in the middle.
I move another pair to the middle, and I now get a triple bond. Okay? Moving the electrons in that fashion allows you to get a better understanding of how our electrons disperse. Okay? In this particular case, it's carbon versus carbon. We don't see a real big difference on where we should place the electrons, so we can just get away with placing them almost wherever we want and kind of getting away with it. But when we switch it up to something else, carbon, hydrogen, and oxygen, now our rules are going to shift a little bit. Okay? We placed electrons on our carbons pretty swiftly and quickly, and that was mostly because carbon is more electronegative than hydrogen. Okay? Whether you believed it or not, that's what you did. Okay? What you might have done instead is say, well, carbon needs more bonds, so I'm going to give it more bonds. Okay? That's a wrong philosophy with a correct outcome. What happens if we move to something like C2H6O? Okay? If I start to build out that structure, what we'll find is that, number one, it gets really complicated really fast with how we could build this. Okay? We could follow the same kind of patterns that we've been seeing. Remember we had C2H6, right? That was this one. But I need an oxygen. Can I bond an oxygen in there? Not with that. So what does that mean? Yeah, like that. Something's wrong. That's okay. Okay, there's really only 2 somethings in here. I have carbon to hydrogen and I have carbon to carbon. Which something is wrong? It's a nasty question. Doesn't matter. Take your pick. Which something do you want to say is wrong? Carbon to hydrogen or carbon to oxygen? Sorry, carbon to carbon.
Carbon, carbon.
Okay.
So when oxygen go between the 2 carbons
Okay.
in the center?
So I'm going to put the oxygen there. I now have all of my atoms. Do I have my octet? how can I,
This might go off a little bit, but isn't there some type of rule with certain things not being able to have double bonds and certain things have to have double bonds?
no. Okay. So the formation of a double bond comes necessarily out of drawing out your structures, okay? From having properly totaled the valence electrons. So where you might have incurred that rule is from an instructor in the past that didn't follow this rule set, but knew the answer for the structure and said, oh, when you have this atom connected to this atom, you always make them double bonds. Bullshit, you don't. Okay? You make double bonds because you have an issue within this process that resolves itself. Okay? Could we have double bonds? No, because if I put a double bond here, I exceed the octet on the carbon. If I put a double bond to any of the hydrogens, I'm going to exceed the octet on the hydrogen. Okay? So how do I fix this?
Put the lone pairs on the oxygen.
How do you know you have lone pairs?
You count out the valence electrons. The extras.
Okay? Which is the answer I want, but what I want to try and drive to is ways that we can avoid having to do this work. 4 times 2, 8, hydrogen, 1 times 6, 6, oxygen, 6 times 1, 6. Did I do that right? 12 and 8, 20. If we look at our drawing, we have 2, 4, 6, 8, 10, 12, 14, 16 electrons in there. To get to that 20, I'm missing 4 electrons. Where are those 4 electrons? They're on the only atom missing the octet. 2 dots. Okay? And this is where I want to touch back to your point. Okay? You said lines, add more lines. I don't want to make these lines, I want to make those dots. Okay? There are instructors that show those as lines. I disagree with that philosophically. These electrons are not involved in a bond. They have very different chemistry than the electrons in the bond. Because they have different chemistry, I want my notation to look different. Okay? Kind of make sense? Okay. So is there something else I could do behind this so that I don't have to count the valence electrons every single time? In Gen Chem, we try to shy, or should be shying away from giving you kind of cheats and shortcuts, because you're responsible for the entire flippin' periodic table to draw things out. That's a lot of things to go through. You should have a solid rule set to move through. We're not looking at the entire periodic table. We're looking at a very small portion of it. We already gave a simplification for carbon. It needed 4 bonds. How many bonds did oxygen need?
6.
It had 6 valence, which meant it needed 2 bonds. But to achieve its octet, I have to get all the way up. There's my last 4 electrons. So oxygen, when it is neutral, will have 2 bonds and 2 lone pairs. Carbon, when it is neutral, will have 4 bonds. Kind of, sort of? So we could start to, in theory, do enough practice behind this that you recognize the patterns and just go, oh, every time I see this, this is what I need to draw. Does that kind of make sense? Which is sort of the intent, as I draw on eraser, of that last one, is now bringing in nitrogen and saying what other things could we go through and do. Okay? As we address that, did anybody have potentially a burning question about carbon having 4 bonds? Okay, my turn. I have a burning question about carbon having 4 bonds. What did that structure look like? That was that, right? Does it have 4 bonds? Does that mean my structure is wrong? No. So there's exceptions? I don't know how to call it exceptions. When we say carbon has 4 bonds, we're saying carbon has 4 bonds when it is neutral. Is it neutral? No, it's positively charged. Which means you could now add another thing to memorize. Oh, when carbon has 3 bonds, it's positively charged. Okay? And that might be a decent conclusion to make until, of course, we try something else obnoxious. Okay? If we make it negatively charged, we now have an issue. Carbon, 4 electrons. Hydrogen has 1. There's 3 of them. We have that charge. It's negative, so what does that mean I have to do with my electrons? Add 1, which means my total electrons is 8. How many electrons am I drawing? 6, which means not complete. What do I need to do to fix it? I can't add another bond. Add a pair of electrons to the carbon, making it negative. Ta-da. How do we know it's negative? This is the formal charge stuff that we could go through and do. We could also say, well, dude, it was negative to begin with. Yeah, that's a good reason too. Okay. How many bonds did we say carbon needed to be positively charged?
3.
Boy, it's negative. That's right. Okay. When you generate rules of like, oh, carbon when it's positive has 3 bonds, I'm going to memorize that. That was true when you tested carbon being positive. But their carbon could be a different charge and could break your rule set. So there's a lot of patterns and things that students will find as they go through and discover more about organic chemistry. And they'll come, oh, carbon always has this. And it's true in that experience. But there's so much other experience that you don't have that the thing that you've now memorized as a rule could entirely be useless. Okay? So you've got to be real careful. If you're going through something, you're like, ooh, I think I found something that I could memorize to make my life easier. It's not a bad idea to run that by me. Okay? Because if you ran this by me and said, well, carbon always has 3 bonds and it's positively charged, I'll be like, well, what's this structure then? Oh, but it's not positively charged anymore. So you have to remember those kind of secondary patterns. Kind of make sense? This is one of the reasons why I don't like just brute memorization. I like a memorization of a process, because that process, when used, will solve things better. Kind of, sort of? Okay. A couple quick things that I want to tackle. When we looked at the C2H6O, okay, we drew it out as C2H6, and then I said that there were 2 options. When we looked at it, there were only 2 things that could have been wrong. It was either the carbon-carbon bond or the carbon-hydrogen bond. I was hoping you said the carbon-hydrogen bond, because that one was easier to do. The carbon-carbon bond meant I had to erase stuff. If the carbon-hydrogen bond is incorrect, what does that mean? There are 2 valid ways to draw this formula. Does that become important? Yeah. You drink this, it's a good spring, what's that thing? Spring break, there we go. It's a good spring break. You drink the other molecule, you're dead. Okay? So structure is very important, formulas very much less so. So one of the things that we'll start to introduce is that we don't want to use raw formulas. We want to use formulas that add some information into this. This would be CH3, CH2, OH. Note I'm showing some of the bonding characteristics behind that pattern. The other one would be CH3O, CH3. I'm adding some more information. They're still formulas, but they're not just a simplified formula. Okay? I also hate formulas. The only reason formulas come into existence is because of typewriters. That's it. Okay? That's why we have formulas. Okay? If I'm trying to ship this information to somebody else, it's a hell of a lot easier to type this in than it is to type in that structure. Okay? So I have every confidence that formulas and kind of unfortunately naming, nomenclature stuff is going to disappear within the next, I don't know, I would hope like 10 years, but
maybe 50 years, because we have the ability to draw structures much, much faster. Okay? And we can transfer that content without having to type up a formula. Okay? But when you look at any textbook, you're going to see lots of typed formulas. You have to kind of learn to kind of deal with those interpretations. The last big thing I wanted to get to, or wanted to show you, apologies for the skipping wildly. Did I pass it? Nope, not yet. Where'd it go? Oh, come on. Please say it's here. There it is. The point of Lewis structure is to get to this. Right? So if you're like, F Lewis structure, I don't want to do the practice. Bad idea. Right? But if you get to this, that'll help you out a lot. Okay? Because this is showing your common bonding patterns. If we have a neutral carbon, 4 bonds. If we have a neutral oxygen, 2 bonds and 2 lone pairs. A neutral nitrogen, 3 bonds and a lone pair. Okay? Kind of make sense? Okay. With that, I absolutely have to be done. I will get to double bonds, multiple bonds, and resonance, which is a really tough concept to deal with, on